When we apply a function to a record value, we need to match up the function's type with the record's type. So in this case, we have a function that expects a record with the x field mapped to int, and the argument here matches. So we can conclude overall that this function application expression has the type int, and we do that by using our rule for function application, which says that if we apply E1 to E2, this is well typed at tau3, provided that E1 has a function type from tau2 to tau3, and that expression E2 has a type that matches the function's input, tau2. So far, so good. Now, what if we try this example? We've got a function that is expecting a record with x mapped to int and y mapped to int, and we supply a record where y maps to int and x maps to int. This seems like it ought to work, but our rule right now rejects it. There is no type for this function application. And the reason for that is we're looking for an exact match between the argument's type and the function's input type. And we don't have an exact match right now because those fields have been reordered. On a similar note, if we've got a function that expects a record with x mapped to int, and we supply a record with an additional field, so x mapped to int, but also y mapped to int, our current rule will reject this application. And again, the reason is because that argument type is not an exact match with the function input type. This motivates subtyping. Nothing will go wrong if our previous function applications were well typed, but our type system is too strict right now, so it's rejecting a value that's perfectly compatible with what the function asks for. So let's use subtyping to get some extra flexibility. We'll say that tau is a subtype of tau prime and write that with this less than or equal symbol, if and only if it's the case that an expression of type tau can be used any place that we're expecting an expression of type tau prime. For example, a record with x mapped to int and y mapped to int is a subtype of a record with x mapped to int. Any place that we're expecting x mapped to int, we can use this record with additional fields instead, and nothing will go wrong. We've got more information in this y field, but we're not using it. Also, if we reorder the record fields, then we should also have a subtype. So with y mapped to int, x mapped to int, that should be a subtype of x mapped to int, y mapped to int. Again, because any place that we expect an expression of this right-hand side type, our code will be perfectly happy if it receives something with the left-hand side type. If the left and the right side types are equal, in this case x maps to int, x maps to int, then they should also be subtypes of one another. And here's one non-example. If we're expecting a record that has x and y fields, but we receive a record that has only the x field, well, this left-hand side type is not a subtype of the right-hand side type. Because if we had a function that depended on the right-hand side type, it might ask for the y field, and our code would go wrong if it received a value from the left-hand side type. The intuition is that two types are in a subtyping relation if there are fewer values in the left-hand side than there are on the right-hand side. So the right-hand side is a bigger, more general type. For records, this means that we have fewer fields on the right-hand side because more fields means more constraints, which means fewer values fit inside that type. At first, it might seem a little backward. We have more fields on the left, but it's somehow less than the one on the right. And it's because we have to think in terms of values and constraints. This is a more permissive type on the right, and this is a less permissive type because it requires two kinds of fields. Here's a subtyping rule for records, and this is capturing just what we said on the previous slide. So a record with x's and taus is a subtype of a record with x primes and tau primes if there are fewer fields on the right-hand side. So these x primes are a subset of the x's. And then on the subset of fields that both records contain, we have to make sure that the types are equal on the left and right-hand side. Now, we also need subtyping rules for our other types. So we'll say that int is a subtype of int, Boolean is a subtype of Boolean, and two function types are subtypes if their left-hand side and right-hand side match. This will work for now as a first draft, but we'll need to come back to this later. And now we need to use our subtyping relation inside the application rule. So we revise application to say that E1 applied to E2 has type tau3 if the function has type tau1 to tau3. The argument has type tau2, so tau2 does not need to be equal to that argument type, but they do need to be in a subtyping relation. So every value of tau2 needs to be compatible with that type tau1. And now we're in business to check the examples. If we have a function that expects x mapped to int, and we apply a record with an additional field, then that now type checks because the argument on the left has all the fields that we require on the right-hand side. Here's our reordering example. If we expect y and then x, and we pass in a record with x and then y, that's just fine by our typing rule because our xy record is a subtype of the yx record. Here's our counterexample. If we expect an xy record and we pass in just a y record, This is not well typed because our argument type on the left is not a subtype of what the function expects on the right. And if we look at the function body, we can see that this is going to go wrong if we were to run this program. If we got inside the function, it's asking for the X field, and that X field doesn't exist on the argument. So it's very good that we reject this application.